Hi, I'm Jack Buffington for robotbrigade.com. This is another video in my series of videos about the code that is running on the microcontroller in my mapping robot. In this video, I'm going to talk about the PWM code that I'm using. In the propeller microcontroller, you don't have peripherals, and so what you do is you write your own. And basically, you call this bit banging in any other platform. This is really handy because it allows you to customize things to exactly how you want, and also you don't have to pore through data sheets trying to figure out what the heck you have to do to configure something, and you're not figuring out, okay, which pin is this on, and does that conflict with this peripheral, and what if I have this one in there? It's just super easy with the propeller. So let's get into this. I've written this particular program in propeller assembly language so that it can be plenty fast. And the first thing that we need to look at is you need to have these variables in the hub RAM, and they must be in this order so that the PWM code knows what to do with or where to look for its variables. And I'm starting up, I'm setting some various values. I'm using an external crystal with a 16 times phase lock loop, and I'm using the clock in frequency of 5 megahertz. When I call this, I am passing the address of the first PWM. And then that gets stuck into the parameter register, which the first thing I do is I move that into hub address. And from here I am loading the initial PWM values, and I'm setting the cycle at 255, so I'm doing 8 bits of PWM. I can do 4-bit, I could do 6-bit, it doesn't matter. I could do a strange number like have 71 different values that the PWM could be. The propeller makes that sort of thing easy. In my case, I'm counting down to 0 because it's very easy to detect 0. I'm reading which pin things start out on. So in this code, I start on a pin, and then each new pin past that is a PWM as well. I have defined just hard-coded that it's doing 4, but I could always pass a variable for that as well. Okay, so now I am setting up some bit masks for the appropriate pins so that when it comes time to write to the output port, I don't have to calculate that every time. I'm just setting up some initial variables for my code, and I'm reading the clock frequency so that I know how many clock cycles happen per second. And I'm figuring out an initial delay. So right here I'm just shifting the clock frequency by a certain amount, and it works out to be about 2000 Hertz if I shift right by 19 bits. I will get into what this is about very shortly. So I saved that value in delay, but I've always had this feeling that it would be fun to try having my PWM be to not be on the same frequency at all times. So when you listen to a robot or any device that's using PWM, and they're doing their PWM in an audible range, you know, it just sits there and squeals. You can just hear it, you know, all the time. And that I find pretty annoying. So I thought, why don't I spread it out, add some noise to the duty cycle, not the duty cycle, to the period of the PWM, so that it would spread out that sound. So if I did a Fourier transform of it, instead of it being flat and then having a high peak and then going down, take that peak and spread it out to a range of frequencies, but they'd all be lower in amplitude. So that's what I'm doing here. I'm using a linear feedback shift register to add a certain amount of timing jitter to the period. And in this loop, it runs 256 times per cycle, I guess you would say, per period. And each time I'm just randomly adding a certain amount of time into it. Let's see now. It is doing this right here, so it's decrement jump if not 0. If it's not 0, it's going to jump to PWM 01, which is down here. If it is 0, then what I do is, and I say I'm decrementing the PWM cycle. So originally I set that at 255, and then it'll go all the way down to 0. If it is 0, I load 1 of the 4 PWM values each time, so that it takes a while to read from hub RAM. So I'm spreading out the reads so that it's not adversely affecting the flow of the code. And then I am incrementing the hub address and incrementing which PWM pin it would be on. And if I've reached the 4th one, then it jumps back down to the first one. Now I am figuring out the actual pin state for the given time slot. I'm comparing the PWM cycle to the PWM value. So this is the value that I want. So if it's 255, it would just always be high. If it's 0, it would always be low. And let's say if it's 128, it would ideally have a even amount of time between the two. Because of my jitter, that is not necessarily true, but it evens out so that on average it is true. So I'm doing the compare, and if this is kind of like you could think of it, if PWM cycle is greater than PWM's, or possibly lesser than, I can't remember the exact truth table to this, then the carry will get set. If the carry is not set, it will add a 1 in the appropriate location to a bit pattern that will be written to the output port. And I do that for all 4 PWM pins. And then finally, I moved those output pins to the output register. And the way things work on the propeller is that each core has an output register, and the final value that's output to the port is the AND of all of those. So I am not interfering with any other register if I write a 0 to some pin and the other core has a 1 on there. The final value will be a 1. Finally, I jump back to loop, which is way up here. And that's it. My experience with this randomized PWM is that it does make the squeal more tolerable, but it's still there. I was kind of hoping it would sound more like white noise, but I guess I was a little too gun shy to give it as much range to vary the timing as I'd need for that. But it does spread it out. It makes it less annoying, and I'm sticking with it because I kind of like it. So that does it for PWM. For robotbrigade.com, I'm Jack Buffington.